Hello, my name is Cole Seeley, and I'm working under Dr. David Dixon in his Computational Chemistry lab under a project titled Predicting Acid-Base Properties of Hydrogenated Halomethanes. This work is in collaboration with Dr. Vittorio Pace at the University of Torino in Italy, and I'm also working under a graduate student named Dalton Andres. So, what is a halomethane? A halomethane is a 5-atom molecule with a carbon in the center containing only halogens and at least one hydrogen at each of the other positions. And for the purposes of this presentation, whenever I refer to a halomethane, I'm speaking about a hydrogenated halomethane. So halomethanes, especially chlorofluorocarbons, possess many industrial and commercial applications. They were used in refrigeration, air conditioning, solvents, fire extinguishers, and even propellants and aerosols. They're extremely relevant to the environment. Some function as greenhouse gases, and others function towards ozone depletion in the atmosphere. And they also occur naturally in marine environments and as a part of certain biological processes. So in order to predict these properties, we're using computational chemistry. What is computational chemistry? So essentially it uses computing power to aim to solve the Schrödinger equation for different chemical systems. In a very simplifying description, this involves the use of basis sets, approximations, and methods. This equation listed here is the general time-independent Schrödinger equation, where H is the Hamiltonian operator, which corresponds to 3 terms: electron kinetic energy, electron-electron repulsion, and electron-nuclear attraction. E is the total energy of the system, and psi is the wave function of the system. While analytical solutions to the equation are known for the very simple chemical systems, in order to solve this equation for more complicated systems, such as the halomethanes, approximations need to be made, such as separating nuclear and electronic motion, approximate treatment of electron correlation, and using an incomplete basis set. Next, methods are the approaches used by the computer to approach solving this equation. And basis sets are sets of functions used to describe electrons in their atomic orbitals. An example listed here is AUG, CC, PV, TZ. So these are the methods that we used in our research. The first being density functional theory, and under that, B3LYP. So DFT describes the energy as a function of an electron density cloud, and it tries to balance accuracy with efficiency, with the computational requirements scaling as iterative n to the third or n to the fourth, where n is the number of basis functions. Next, post-Hartree-Fock method, we used MP2 and CCSDT, where MP2 is the simplest treatment of electron correlation, scaling as n to the fifth in terms of computational requirements. And CCSDT, also known as coupled cluster calculation, is much better a treatment of electron correlation, scaling as iterative n to the sixth and non-iterative n to the seventh for that parentheses t term. Next, G3MP2 is a composite method, which means that it combines MP2 and CCSDT with varying basis sets in order to provide a high accuracy with a reasonable computational cost. And then, in order to do some of these calculations in an aqueous solution, we have to use a solvation model based on density, or SMD. And this falls under the category of implicit solvation, where the solvent is represented by a continuous polarizable field with a dielectric constant. So here are some of our results. This is a table of delta G acidities of halomethanes in the gas phase in kilocalories per mole. You can see with the experimental values on the right-hand side gathered from NIST that our calculated theoretical values are extremely close, falling within either the experimental error of the values or within 1 kilocalorie per mole, which is the chemical standard for accuracy. You may also notice that CH2F2 is an exception to this. However, FPD, or Feller-Peterson-Dixon method, very high-level theory calculations, show that this experimental value is likely incorrect. So what is a delta G acidity? Delta G acidity corresponds to the reaction in the bottom right-hand corner, where the neutral species undergoes a heterolytic cleavage in which the hydrogen dissociates without its electron, so dissociating only as a proton and forming the anion species. So as a reference, H2SO4, or sulfuric acid, has a delta G acidity of around 304 kilocalories per mole. So all of the species here have at least 30 kilocalories higher delta G acidity than that. You can also think of kilocalories as the same unit used on nutritional labels. However, on nutritional labels, they list it simply as calories. In terms of trends, you can see that as methane becomes more halogenated, delta G becomes smaller. And this is because the halogens are very electronegative, which increases the stability of anion species. You can also possibly see that there are blanks in the G3MP2 column for those molecules containing iodine. And this is because we are still working on them. Iodine is a difficult atom to deal with G3MP2. So in terms of how close our values are to the experimental values, this gives credibility to say that most of the values that do not have corresponding experimental values can be used as references in which we calculated. Next, this is a table of pKa values, which are calculated using our previous delta G acidities, along with combining that with the aqueous SMD calculations. So a pKa is a measure of the acidity of the molecule. Lower the pKa, the higher the acidity, and the more willingness for the species to dissociate its hydrogen in a solution, where the solution is water in this case. So here you can see that the experimental data is extremely sparse and very approximate as well, with one even being listed as a range of 6 pKa units. Again, that same trend persists here, where halogenation of the halomethanes increases the acidity or lowers that pKa. And with our credibility from the other data, all of these values are able to function as references for chemists around the world. Here we have electron affinities and bond association energies of halomethanes at G3MP2. These are calculated using radical species calculations, and it corresponds to the reaction in the bottom right-hand corner for bond association energy as a homolytic cleavage, where instead the hydrogen dissociates with its electron as opposed to heterolytic cleavage. Here I would also like to point out that there is a unit change from kilocalories to kilojoules per mole. And you can also see that those experimental values with the A superscript are considered extremely accurate, and our values are either within that experimental error of around 1 kilojoule, or with the exception of methane, within 1 kilocalorie, which is still within the chemical standard of accuracy. This credibility, again, persists and shows that all of these values, which do not have corresponding experimental data, which is the majority, our calculated values can serve as references. CH bond association energies can also allow us to calculate thermodynamic cycles along with previous data, and electron affinities along with aqueous phase calculations allow us to calculate redox potentials. So as a summary, our work provides the most complete set of gas phase acidities, pKa's, electron affinities, and CH bond association energies for the hydrogenated halomethanes. Higher level Feller-Peterson-Dixon calculations for CH2F2 show that experimental data needs revision. And there's excellent agreement with the experimental values for all properties suggesting similar accuracy for species without experimental data. And finally, in terms of future work, we're going to complete the calculations for compounds with iodine atoms using a modified G3MP2 approach and calculate redox potentials using radical species solvation energies. Here are my citations. Thank you for listening to my presentation. Any questions?
Can you go back to slide 5? Can you give us a little bit more of appreciation of the empty spaces in the G3MP2 on iodine atoms? Is it a computational power problem, or is it just the complexity of the process itself? Can you say a little bit more about why that's the case?
So in terms of those blanks, the reason why iodine is difficult to calculate with G3MP2 is because G3MP2, the standard method is to use a basis set known as 6-31GD, and this basis set is too small to account for iodine, which is a very large atom and has 53 electrons.
Looking at this table, I can conclude that simplest DFT
case, and has the ratio of requirements to accuracy is still better for G3MP2. However, in terms of other calculations and such, you would have to ask my project director as he's more knowledgeable in the topic.
Can you explain each of the parts of the basis set example you gave on, I think it was slide 3? Like, what do they mean?
So this basis set example, AUG-CC-PV-TZ, stands for Augmented Correlation Consistent Polarized Valence Triple Zeta. So the augmented term here says that the basis set includes diffuse functions, which account for electron density far away from the nucleus. Correlation consistent tells us that this is a Dunning type basis set and is specifically designed for electron correlation. And polarized with the word tells us that there are added polarization functions. And finally, valence triple zeta tells us that there are 3 sets of basis functions used to describe the valence orbitals.